be 0. This is what is known as the Clausius theorem. Okay, what is the relevance of proving this to the concept of entropy? That we will discuss. Need to be clear on what we are going to prove. Okay, it would be a sort of mathematical treatment, and you might find it too mathematical and sort of bereft of the actual world, okay, real world. But after we go on to prove mathematically and logically that there exists a property called as entropy, okay, then we would take up the insightful discussions. Okay, I mean to say, I would try to relate this concept to the real world. Okay, but for the time being, the plan is to just go about deriving this expression, what is known as Clausius theorem. Okay, as you have seen in the videos, we would be using two steps for this proof. One is, first we would be proving that any reversible path. Okay, first what we would be proving that any reversible process, I'm not talking about cycle, please note, any reversible process or reversible path, what I would be proving first, okay, can be replaced by set of three processes. Okay, replaced by set of three processes, which would give us some sort of a zigzag path. Okay, a zigzag path comprising of three processes. And what are the three processes? The three processes of the three processes, two would be reversible adiabatics. And because we have already proved that these two reversible adiabatics cannot intersect with each other, so there has to be some process in between. Okay, so what we would be proving is that if you consider any reversible path, then that reversible path can be replaced by a zigzag path comprising of three processes, of which one is a reversible adiabatic process, followed by a reversible isotherm, and that again is followed by a reversible adiabatic. Okay, it means that uh, you can, if you consider any reversible path, then we can show that that reversible path is equivalent to a set of three processes comprising of two reversible. So let me draw. Yeah, am I audible now? Okay. Rushikesh, am I audible now? Okay, thank you, Rushikesh. So if you don't hear me, okay, I am going extremely slowly. I am accounting for all the network issues. and I'm going extremely slowly so that you appreciate what I am telling you. Okay, and I will be repeating the points again and again. This is to make network issues. Okay, so I understand that there could be a lot of disturbances while viewing this video. Okay, so I'm moving extremely slowly. So what I am drawing is I am considering a reversible process. Okay, what I want to prove? I want to prove that Ankit, am I clear now, Ankit? Ankit, am I clear? Okay, thank you. So what I want to prove now is to prove that what is to be proved, that a reversible path, a reversible path, a reversible path is equivalent to a zigzag path. Okay, comprising of three processes of which two are adiabatics and one is isotherm. All are reversible. We are talking about reversible. Okay, this is to be proved. Okay, now let us say that this is the reversible path under consideration. This is the reversible path under consideration. Okay, so let me call this as some initial state I to final state F. So this reversible path is from I to F. Okay, this is the reversible path. Now what I want to prove is that this reversible path can be replaced by reversible adiabatics. Okay, so let me draw adiabatic lines. So this, you know that this would be adiabatic lines. Okay, so let us say this is adiabatic, this is adiabatic. Okay, right? So this two which I have drawn, these two are reversible adiabatics, and you see that I have drawn them parallel, making use of the fact that two reversible adiabatics cannot intersect with each other. Okay, so what I have drawn is two reversible adiabatics. Okay, and they are drawn at the ends. Okay, that is at the state I and state F. Okay, so let me call this as reversible adiabatics as reversible adiabatic IA, and another reversible adiabatic BF. Okay, BF. So let us say this is A and this is, let's say, B. Okay, this is B. Okay, and I need to draw them such that, okay, let us say this is B. So this is A, B, F. Okay, so I need to draw these lines. Should be drawn such that the area, okay, they should be drawn such that the area under IABF is equal to the area under I2F. Okay, should be drawn such that the area under, okay, what is the condition which is to be satisfied? The condition to be satisfied is that the area under IABF has to be equal to area under I2 F, I to F. Okay, it means that the area under the zigzag path, has to be equal to the area under IF. Whether this is understood? I'm pausing a bit and asking you this question. Whether this is understood? You can answer in yes or no. Whether this is understood? Yes or no? Or you want me to repeat this? Ritesh, it's understood? Nikhil, yes. Ankit is saying yes. Do you want me to repeat this? Vedant, it's understood or repeat? Okay. Raju is saying I need to repeat this. Okay. Even if one of you has not understood, I will repeat this. Okay, okay. Parikshit has understood this. I will repeat this. Doesn't matter. Repetition is not an issue. See, once again, what we are going to prove? We are going to prove that a reversible path, which is I to F. Okay, this is I and this is F. This is F and this is I. Okay, so a reversible path I to F can be replaced by a zigzag path comprising of three processes. One of the process is reversible adiabatic, and that is I to A, followed by a reversible isotherm, which is A to B, reversible isotherm which is A to B, and the third process is again a reversible adiabatic, which is B to F. Okay, we want to prove that this I to F is equivalent to, it is same as three processes. Okay, means in other words, if any reversible path is given, then I should be in a position to replace that reversible path by these three processes. Okay, by these three processes. I hope now it is understood. Okay, this is to be proved. Now for that, what I need to do is that I need to select the reversible adiabatics in a manner such that, okay, the area under IABF, okay, IABF is the same as the area under I to F. Okay, so this can be, you can think of one diagram on a pressure volume plot, where you can draw it in a manner such that you can keep this area under I to F equal to the area under IABF. Okay, it's a matter of construction. I have not drawn it proportionately, but you can draw it in your notebooks and make sure that the area under IABF is equal to area under I to F. Okay. So what does that mean? What does that mean? Area under IABF is equal to area under IF means, it means that work. Okay, it means that we are considering these processes in a manner such that the work during the is equal to the work which is obtained, the combined work which is obtained by the set of three processes I, A, B, F. So work of IF is equal to work of IABF. Why is that so? That is because we have drawn the three processes such that the area is the same. Now let us apply. Let me rub this first, because it is. Let me rub this first. And now I am going to apply the first law of thermodynamics to the reversible process I to F. Okay. first law of thermodynamics. I'm going to process I to F. Okay, let me rub this first. Okay, now it is clear. So let me choose another color. Okay, right. So let us apply the first law of thermodynamics to the process reversible path, reversible path, reversible process I to F. What is the first law, mathematical statement of first law of thermodynamics? The mathematical statement of first law of thermodynamics is Q is equal to delta U plus W. Delta U plus statement of first law of thermodynamics as applied to a process. Okay, it means that Q I to F is equal to I plus W I F. Okay, let me call this as some equation. This is equation 1. Okay, this is equation 1. Let me call this as equation 2. Let me call this as equation 2. Right? Now let me apply the first law of thermodynamics, to the zigzag path. Applying this, it means you will get Q I A B F is equal to the internal energy of the end states. Okay, final internal energy is what? It is IABF. Okay, IABF. What is the final internal energy? It is UF. And what is the initial internal energy? It is IABF process. So initial internal energy is again UI plus WIAEF. Let us call this as process 3. Let us call this as this process 3. Okay. Now what it means? Look at this. Look at the equations 1, 2 and 3. Look at the equations 1, 2 and 3. What do you get from these equations? What from 1, 2 and 3? What do you say? It is simple logic now. Is equal to WIABF. This terms UF minus UI from the equations 2 and 3 are same. Okay, so WIF is equal to WIA becomes, it means that Q heat transfer during the process I to F, which is the reversible path, 1, 2 and 3. Okay, Manish, right? So QIF is equal to QIABF. Okay. Now let us call this as equation 4. Now please reflect upon the equations 1 and equations 4. Okay. What do you find? We find that if you consider the process I to F and compare it with, the zigzag process IABF, then in the manner which we are considered, then we see that the work transfer and heat transfer are now the same. In the manner which we are considered, the work transfer, heat transfer are the same. In other words, there can be an equivalent path. Okay, there can be an equivalent path. We can draw an equivalent path. That equivalent path is IABF. Okay, to replace what? To original reversible path if. Okay, we can have a particular equivalent path, okay, which can replace the original path. And what is that equivalent path? That equivalent path is a zigzag path comprising of set of three processes, which means two reversible adiabatics not intersecting with each other, mind well, not intersecting with each other, two reversible adiabatics with a reversible isotherm in between, okay. So this is the first part of your theorem proof, okay, that we have shown now that any reversible path if can be replaced by an equivalent path comprising of a zigzag path, okay, comprising of three processes, two reversible adiabatics and a reversible isotherm. So making use of this understanding, the proof, the final proof becomes extremely simple. Okay, so let me now go to the final step of the proof of Clausius theorem. I hope you have understood this. All of you understood this. If you understood this, please say yes. If you understood this, please say yes. Okay. Thanks, Rushikesh, Gargi, Ritesh, Sanket, Gauri, Lucky Singh. Gargi Singh नहीं समझ लो. Okay, Sairaj. I will repeat this, Gargi, don't worry. Akanksha. Let me first complete this. I will repeat this. Akanksha. Okay, all right. Okay, Gargi, I will repeat this again later, but let me first complete this again. Let us consider a reversible cycle now. Let us consider a reversible cycle. This reversible cycle means what? This reversible cycle means it is comprising of, you can think of an infinite number of reversible paths. Okay, this reversible cycle is equivalent to infinite number of reversible paths. Okay, infinite number of reversible paths. Right now, because this is a reversible cycle, and we had shown, what did we show? We had shown that if you consider any reversible path, okay, for example, let me use some other color. We had shown this, that if you consider any reversible path, okay, then that reversible path can be enclosed by two reversible adiabatics. That reversible, this is what we had proved, no? That at the end points, this reversible path would have two reversible adiabatics, and they are all parallel, reversible adiabatics, and they are parallel to each other because they do not intersect with each other. They are parallel to each other. Okay, and in between, you can think of, one can think of a reversible isotherm. One can think of a reversible isotherm. Okay, so there is isotherm. Okay, so this we had proved. What did we prove? We had proved that if you consider any reversible, a zigzag path comprising of two reversible adiabatics and a reversible isotherm in between. Okay, now because it is a reversible isotherm process, it might have Okay, certain heat transfer. Let us say that heat transfer is del. Okay, let me write it somewhere else. Okay, all right. I guess that. Okay. So this, let us say this reversible heat transfer is del Q1, and it happens at a temperature T1. Okay, it happens at a temperature T1. Just a minute. Okay. Whether the whiteboard is seen? It is splitted. Okay, I'll try to adjust it. Before that, I'll put a poll question. Okay, let me try to adjust it. The theorem, as I had already explained you, and we are proving this, that it is applicable to a reversible cycle. It is applicable to a reversible cycle, and it is not applicable to a reversible process. We had, what we want to prove is that cyclic integral of del q by t, cyclic integral of del q by t for a reversible cycle is equal to 0. Is equal to 0. That is what we are planning to prove. Okay, that is what we are planning to prove. Okay, so now let me close the poll and let me go back to our discussion. Okay, are you able to see the white screen? Okay, thank you, Gagi. So what we have done now is we have replaced this reversible path with two reversible adiabatics and a reversible isotherm in between. Similarly, I would be replacing this reversible path, okay, with two reversible adiabatics and okay, reversible. Let me just draw it again. Okay, I'll draw it, don't worry. So we can think of closing this reversible path. Okay, so this again is a reversible isotherm. Let us say that the heat rejected is del Q2 at T2 at T2. Okay, so what I have done is I have taken a small part of a reversible cycle. I have taken a small part of a reversible cycle, and because I know that this small part, which is a reversible path, is equivalent to two reversible adiabatics and a reversible isotherm. I can in a way think of this cycle as comprising of slices. Okay, infinite number of slices. Okay, wherein these slices are enclosed by from the sides, they are enclosed by reversible adiabatic processes, reversible adiabatic processes, and they are enclosed from top and bottom by reversible isotherms. So if I want to draw a magnified view, okay, it would be somewhat like this. This kind of thing. Sorry, let me draw it. Okay, so this sort of thing. Okay, this sort of thing, wherein is this is the reversible isotherm. The heat transfer is del Q1, which is occurring at some temperature, constant temperature T1, and there is a heat rejection. Sorry, there is a heat rejection del Q2 del Q2 at T2 T2. Okay, and and this two, the other two, I mean to say the other two processes. What are those processes? The other two processes are reversible adiabatics. Okay, so this is sort of P representation. So if you look at this, so this small portion which I have taken of this reversible cycle is equivalent to a Carnot cycle. Okay, this is a Carnot cycle. Yes or no? Because a Carnot cycle has two reversible isotherms. A Carnot cycle have two reversible isotherms wherein there is a heat addition. This is one reversible isotherm and this is another reversible isotherm. Okay, let me call this as some A, B, C, D. Okay, so this would be here A, B, C, D. Okay, right? So this reversible cycle is a Carnot cycle comprising of two reversible isotherms wherein heat added is del Q1 at T1 and heat rejection is del Q2 by T2. The efficiency of which is given by 1 minus T2 by T1. 1 minus T2 by T1. And you know that efficiency of any heat engine, efficiency of any heat engine, efficiency of any heat engine is equal to 1 minus del Q2 by del Q1. Del Q2 by del Q1. Okay. So it means so it means del Q it means del Q1 by T1 is equal to del q2 by t2. Del q2 by t2. Okay. Let me repeat this once again. What we are doing, okay, we want to prove. What we want to prove is that the Clausius theorem. And what is this Clausius theorem? It means cyclic integral of del q by t for a reversible cycle is equal to 0. Okay, is equal to 0. This is what is the Clausius theorem, and we want to prove this. Now, how are we proving this? For proving this, we have considered a reversible cycle, which is shown on the board. Okay, red colored cycle, which is shown on the board. And we had proved that. What did we prove? We had proved that a reversible path is equivalent to a zigzag path comprising of two reversible adiabatics and a reversible isotherm in between. So what it means is, if you slice this off, okay, you convert this actual cycle, the actual reversible cycle, you slice this into infinite number of pieces. You slice it into infinite number of pieces, such that the slices would include two reversible adiabatics and two reversible isotherms. Okay, reversible isotherms. So we can imagine this reversible cycle comprising of infinite number of slices. How would a slice look like? A slice would look like what is shown here. A slice would look like what is shown here. Okay, and what is that slice? So that slice becomes a Carnot cycle. One of the Carnot cycle of one of the slice is shown over here, and for this slice I have shown that del q1 by t1 is equal to del q2 by t2. Del q1 by t1 is equal to del q2 by t2. Now, if you consider another slice, if you consider a slice next to it, okay, any other slice, then you can have another Carnot cycle, wherein the heat transfer would be del q at t3 and heat rejection could be del q4 at t4, whatever nomenclature you choose. And you can similarly show that for that slice del q3 by t3 would be equal to del q4 by t4. So this expression becomes now for the second slice. And what is that second slice? That second slice is again a Carnot cycle, where the heat supplied is del q3, heat rejection is del q4, heat is supplied at t3 and heat is rejected at t4. Okay, in this manner we can do a thought experiment, wherein we would consider slice by slice all the Carnot cycles, and have similar expressions. Okay, now when I am saying this is del q2 by t2, I have already incorporated the negative sign over here. Okay, please note, I have already incorporated the negative sign of heat rejection over here. Okay, so what it means is that okay, so this is negative. So if I rewrite this, for the first slice, whatever is first slice, you would say del q1 by t1. This is minus, so it becomes here plus del q2 by t2. Okay, for the second slice, it is del q4 by t4. Okay, plus let us say for the third slice, it is del q5 by t5 plus del q6 by t6. This now you need to continue writing for infinite number of slices. Okay, this you need to continue writing for infinite number of cycles, and this would become 0, because if you solve this, del q1 by t1 plus del q2 by t2 is equal to 0, del q3 by t3 plus del q4 by t4 is equal to 0, like this. Okay, so what you will get is a interesting expression. And what is that interesting expression? It is nothing but This is nothing but the integral, okay, integral over the thermodynamic cycle, a thermodynamic reversible cycle, integral over a thermodynamic reversible cycle of del q upon t, of del q upon t, okay, which is equal to 0, which is equal to 0. So what we have shown is that if a cycle is reversible cycle, if the cycle is reversible cycle, then for this reversible cycle, the summation of all this del q by t, the summation of all this del q by t is equal to 0, and that is what is known as the Clausius theorem. Okay, this is the theorem. I hope that you have understood this. If you understood this, please say yes. If you haven't understood, say no. Okay. If you understood this, say yes. Have you understood this? Yes or no? Okay. Prathamesh is saying has understood. Dheeraj is saying understood. Pranamate has understood. Okay. For Gargi and others, those who had not understood, I would do a quick revision. Okay. I will quickly revise whatever I had told. Okay. Even the earlier proof. Okay. I will be very quick, and I would try to run through the proof. Okay. What we want to prove is listen carefully. Those who have not followed it, you listen carefully. Proof now. It means that I want to prove that cyclic integral of del q by t, cyclic integral of del q by t for a reversible cycle is equal to 0. The step 1 of the proof is consider a reversible path is equivalent to, it is same as, equivalent to means it is same as rising of a reversible adiabatic followed by a reversible isotherm, again followed by reversible at temperature T, at a temperature T. Okay. The audio connection is lost, I guess. Okay. So I to F, I want to prove it to be equivalent to a zigzag path. Now, how do I prove this? I apply the first law of thermodynamics to this. I to F is equal to UF minus UI plus WIF. Okay. I have drawn this in a manner such that the area under I to F is equal to area under IABF. I have drawn this in a manner such that the area under I to F is equal to area under IABF. In other words, I already know that work of IF is equal to work of IABF. This I had called an equation 1. Now, this becomes your equation 2. If I apply the first law of thermodynamics to this zigzag path, it becomes QIABF is equal to UF, internal energy of the end state, minus UI, internal energy of the initial state, plus IABF. This becomes my equation 3. So if you look at equations 1, 2 and 3, what you get is QIF is equal to IABF. Just comparing equations 1, 2, and 3, which is equation 4. Now, if you look at equation 3 and equation 1, sorry, equation 4 and equation 1, you see that in the process I2F and in the zigzag, it means that these two processes are equivalent. It means that these two processes are equivalent. Now, with this knowledge that you can always replace a reversible path with a zigzag path comprising of two reversible adiabatics and a reversible isotherm. You consider an actual reversible cycle, a reversible cycle, and slice them into infinite number of pieces. Okay, and here infinite number of pieces, but you can draw in your notebooks and show very small slices, wherein they are on the sides, they are covered by reversible adiabatics, and they are topped by reversible isotherm. So suppose you consider this this ABCD cycle, right? And let us say that this is some del Q1 at T1, and the heat rejected is del Q2 by at T2. Then you understand that this, what you get is, because by slicing this reversible adaptation, what you get is actually an elemental Carnot cycle. And for an elemental Carnot cycle, del Q1 by T1 is equal to minus of del Q2 by T2. Okay, now I am including the sign, or in other words, for the elemental cycle, del Q1 by T1 plus del Q2 by T2 is equal to 0. Similarly, for this elemental cycle, the another elemental cycle, you can write del Q3 by T3 plus del Q4 by T4 is equal to 0. Some other cycle, del Q5 by T5 plus del Q6, like this, so on and so forth. In other words, you can go on writing this up to infinity. Okay, and this becomes equal to 0. So writing this, summing up is nothing but integrating it over the the way of writing it in mathematics is like this: the cyclic integral of del Q by T is equal to 0, which is called as the Clausius theorem. Okay, and from this theorem, we would be discovering, by proving this, we would be discovering a property called as entropy. I hope that for most of you now it is clear. Okay, even for those who had not understood it. So let me ask you again whether this is clear to you. Let me ask you whether this is clear, whether the proof for Clausius theorem is clear to you. Please respond saying yes or no. Yes or no? Tamesh, Dheeraj. attending this session. Okay, good day.